So the next talk in this session will be given by Ignacio Rozada from 1QB Information Technologies. And this is joint work with quite a number of other people from quite a number of other labs. I will leave you to list all of them with the proper affiliations. And the title of the talk will be In-Memory Optimization Accelerator for Quadratic Assignment Problems, a Hardware Implementation Proposal. So we're looking forward to your talk.
Thank you very much. And thank you very much to the organizers for inviting me to give this presentation. I'll get to my collaborators in my last slides. I want to say that I come from a company in Vancouver called 1Qubit, and a lot of what we do is solving hard problems with unconventional hardware. And I think this will give you a good idea of the kinds of things that we look into. I was going to dive in right into the problem that we were working on, but I felt the need, after listening to so many very good talks on using neuromorphic hardware on machine learning applications, to motivate our work a little bit more by explaining the types of things that we do towards optimization and why one would want to build custom hardware for these types of problems. I want to point out that there are many very high-value optimization problems. I'm talking billions of dollars of budgets per year. I heard in a couple of talks before that hardware and software verification are considered some of the hardest problems to do. We're talking about, for example, the Challenger or the NASA spacecraft, where you cannot afford to build them and crash them until you get the right one. And they're also, as far as very large problems, those are very well known. And there are also very small problems that are also very hard. We all have in our phones a radio that communicates with, nowadays, with 5G and upcoming technologies. There's multiple antennas in our phone communicating with multiple antennas. And there is an NP-hard problem of resolving the signal from coming in. And this is a problem that has to be done in milliseconds with a very low energy budget. So all of these problems require dedicated hardware. In the 2010s, a number of companies started building hardware accelerators. Perhaps the D-Wave quantum annealer is the most well-known. A lot of these hardware accelerators target problems called quadratic unconstrained binary optimization problems. Despite all the excitement that these problems have led, one thing that we've seen is these are not generally state-of-the-art for industrial problems. And we believe that using in-memory compute on hardware, we can build very fast and low-energy problems. So now I'm going to get into the problem that we focus on most, which is called the quadratic assignment problem. It's one of the most well-known and understood hard constraint optimization problems. It has a very elegant objective function. There has many high-value applications. It's a problem of given a number of facilities and locations, and the facilities have flows between them. What is the optimal location of the facilities that minimizes the flow? This problem maps very well to problems like protein positioning. It's fundamental in chip layout design, and there's many warehousing applications that map directly to QAP. Now, why one would want to build a hardware accelerator for QAP? It's one of the problem is it seems like it would be a good fit for a QUBO solver, given that it's a quadratic problem. It also has a feature that small problems already are very hard. You cannot solve them. Even problems of 30 facilities, you cannot solve them with an exact general-purpose solver. And state-of-the-art heuristics to solve these problems are relatively simple. They only rely on local search. And this is why all of these companies that build QUBO hardware have been trying to tackle this problem. However, there are hard downsides on formulating your problem as unconstrained binary optimization problem. And this is that there are hard constraints on the problem. One facility has to be only on one location. And typically, you deal with these constraints by adding penalty terms. And the downside of this, or one of the many downsides, is that your solution space is already large. It's n factorial in the native space, and it blows up exponentially when you have to consider a number of infeasible solutions. The QAP constraints, again, are incorporated as penalized terms in the solution. And I'm not going to go into details, but what happens is that to go from one feasible solution to another feasible solution with with single bit flips, which is what you would normally do in a vanilla QA solver, you have to go through necessarily at least 3 infeasible solutions that are going to be penalized. So you end up with a problem that has a very rough landscape. And this has also the added issue that the penalizing terms adds bits of precision requirements on your hardware. I'm just going to quickly show some results. We did a simulation where we compared solving a QAP problem in its QA formulation with a very tuned solver with Taboo, for the people that know Taboo. And we compared it with a native solver using Taboo and just randomly generating feasible solutions, which is cheap and easy on QAP. And what we see is that the QA formulation only finds a very small number of feasible solutions, and generally stays a very far away, in a faraway distance from the optimal solution. And our simple native solver with Taboo finds the optimal solution in relatively few iterations. This more generalized example shows for multiple problems how solving the problem with these QA solvers doesn't really differentiate or improve much on randomly generating solutions. This is a comparison that we did against what I think is the state-of-the-art effort on using a very sophisticated QA solver. This is an effort for a group within Google where they really threw everything at the problem. They did 10 to the 8 iterations of an adaptive parallel tempering solver. They did significant hyperparameter optimization. And when we compared it with a few different meta-heuristics on our simple solver, with default parameters, we found already much better solutions. And with a bit of parameter optimization, we were able to see the optimal solutions right away. And perhaps the key point here in the middle part of my talk is that I want to argue and convince people that it's pointless to solve problems such as quadratic assignment and this applies also to other constraint problems with a QA solver by penalizing, just because the penalty that you pay trying to find these feasible solutions or navigate this huge exponentially larger space is too expensive. There is a caveat here, and this is that in the way that I said that there are 3, you need to jump over 3 infeasible solutions to go to another feasible solution. It could be possible to design a heuristic that does this automatically and just keeps jumping over the infeasible solutions and always lands on a feasible solution. And at that point, you don't have to penalize anything. You don't have to pay the cost on added bits of precision due to the penalty terms. But you need to do this very efficiently. And this is sort of a method that we came up that achieves this process. A QA solution feasible QA solutions are permutation matrices. The QA solution is really, you just extend it into an array. And what you do first is we look at the indices of the entries in the QA solution that are 1s, and we store all those indices in an array. And then randomly, we're going to choose 2 of those x = 1 indices. And these are the first 2 bits that we're going to flip. And then if you look at the matrix, these are the 2 terms that we flipped, and we need to go back to a permutation matrix. So in some sense, it's pretty clear that we need to flip this 0 here and this 0 here to go back to a 1-hot encoded solution where all the rows and all the columns add up to 1. You can do this. You can calculate this trivially from from your original choice of 2 values to flip, and then your quadruple flip can be, once you find it, you do it, and you're guaranteed to go from a feasible solution to another feasible solution. Okay, so now what can we do now that we have these feasible moves? Where can we go from that? So we have a solution x0. we randomly select 2 values to flip, and we land in another feasible solution. One thing that we can do is evaluate all possible pairs of bits to flip from the original solution and generate all of the possible, this is called the full neighborhood of possible solutions, and add some sort of criteria to choose that we can, if you want to be greedy, we just choose whichever one of these leads us to the biggest improvement in our objective function. Or we can add a more sophisticated meta-heuristic to escape local optima. Local optima are a big issue with quadratic assignment problems, even in its native formulation. I'm just going to show here quickly to see the power of these full neighborhood iterations, where we can evaluate all possible solutions and always go towards the best one. We can see that for these 9 QAP problems of different sizes, within a few iterations, within 10 iterations, we've already decreased the residual from the best known solution or the optimal solution dramatically. And in fact, if you look at the iterations here, in average, you tend to hit a local optima in about 20 iterations or so. So it's critical to have a meta-heuristic that allows you to escape this local optima, be that annealing, taboo, simply doing multiple repeats. One thing that we need to do when dealing, if our hope is to use neuromorphic hardware, is to address some of the limitations, particularly precision. So we looked at quantization of the different problems down to, let's say, 8 bits, 6 bits, 4 bits, and 2 bits. And we see immediately that if we do a simple affine transformation of the matrices, this is very problem dependent. Some problems you have very little changes, but in many problems, even going down to 8 bits, you lose over half of your non-zero terms in the problem. And our question was, if we do quantization, how does this affect the dynamics of our heuristics? And surprisingly to us, the solvers behave relatively well under quantization. You can see that the no quantization scenario in blue doesn't differ very much from 8 bits, 6 bits, and even 4 bits. Let me just highlight the 2 biggest problems that we have here and zoom in on those problems. And you can see that 6 bits and 4 bits are pretty solid on this problem. It's not a guarantee. There may be bigger problems or different problems, or it could depend on the original sparsity of the problems. But this is very encouraging for us. And here I want to show some solutions that we did, comparing to what we found to be the state of the art on solving QAP. This is hardware. The PBM64 is a 64 core parallelized parallel tempering heuristic from 2020. There's a slightly newer version of this where they run it on FPGAs, and they have maybe a 5x improvement. Pari-OTS is a combined genetic and taboo heuristic. And here, what I'm considering 2 scenarios for our solver, which is a parallel tempering implementation. This is a simplified hardware model that goes 5 nanoseconds and 50 nanoseconds per iteration. But I am assuming here that these full neighborhood evaluations, where for each solution we evaluate all possible perturbations to the solution and we choose the best one, this is done serially. So we do each one in series, and it adds up to our timing. And we expect to see an improvement, at least within these parameters. Perhaps not so much on the larger problems, but not something completely dramatic. However, if we, instead of assuming this serial evaluation of all the full neighborhood, it is possible to evaluate it in a single parallel iteration using memristor hardware. And in this case, if you take a look at the hardware model that we used for our runtimes, even within 3 orders of magnitude range, we see significant advantages over these other state-of-the-art solutions. So this was the gist of my presentation. I think the takeaways that I want you to take out of here is that QAP itself and in more general other optimization problems certainly also are high-value optimization problems. This one has a feature that there's very simple heuristics that give you the state-of-the-art results on solving this problem. This is a problem that is simple to map to cuboform. However, if you do it naively, you're going to pay a huge penalty and not be anywhere near fast solvers. However, we think that it's possible to build a performant QAP solver by using a trick to avoid all of this invisible landscape. And it turns out that this heuristic appears to be robust against quantization. And some evidence from other projects from our team makes us optimistic about this problem, both on time and hopefully also on energy usage. And I just want to highlight here, this comes from a collaboration with people from HP, ULIC over here, and UCSB. And this is from a project funded by DARPA. Thank you very much.
So thank you very much for this very nice talk. Are there any questions from the audience? And while people are getting to the microphones, maybe let me start with the question. Whenever you build a hardware accelerator, you really focus on some key steps to improve. So from what I gathered, the core step is this two-swap move that you would focus on making more efficient. But then you also have the meta heuristics, and they differ between different solvers. So how much would you focus on specific meta heuristics, and how much of the design would be general to accommodate different solvers?
That is a very good question. There are many different meta heuristics that one can use, and they can have a very significant impact on your solution. One of the approaches that some people are very keen about is, given that there are many meta heuristics and it's a complicated problem for you to decide who's going to say that you are the one that's going to know which one is best. In many cases, and this is the case on, for example, this Pari OTS, what they do is they take two different meta heuristics and just combine them and run them in parallel. And in fact, they can combine solutions. So it's possible to use portfolio solvers where you have many different meta heuristics, ideally some that are not correlated, and even train a model to help you decide which one is the best one to use for that.
OK, thank you. Are there any more questions from the audience? If not, then let's thank the speaker again.